Welcome back to electrochemistry. In part 4 of this unit, we're going to be looking at electrolytic cells and Faraday's law. Let's get started. An electrolytic cell is a non-spontaneous reaction made spontaneous by the application of electricity. So instead of in a voltaic cell, the voltaic cell is a battery, the electrolytic cell needs a battery. It requires a battery to function. Without a battery, nothing will happen. So we're making a non-spontaneous reaction spontaneous. So one common application of electrolytic cells is electroplating, or plating of one metal on top of another. So we're going to diagram an electrolytic cell. Something that you're going to notice about the diagram of an electrolytic cell is that it's got one beaker instead of two. And let's hook this up. And this right there is a battery with a positive terminal and a negative terminal. Let's put that back where it was. Okay. So we'll have some aqueous solution, and in this one we're going to have a copper aqueous solution because we're looking for copper plating. So this metal will be copper metal, and there'll be copper ions in solution. And we'll say that that coin there, that cent, is going to be a zinc coin that we're going to put copper on top of, commonly how they make actual pennies. They're made out of zinc and then plated in copper on the outside. So what's going to happen is, if you look at copper, plus 2 electrons on the reduction potential chart, copper is higher than zinc, which means copper should be the one that's reduced because it's the one that's higher than zinc. Oops, I see that I did that. But in an electrolytic cell, it's a non-spontaneous reaction. So the one that's higher is actually the one that's going reverse instead of the one that's lower is going reverse. So instead of having copper plus 2 turning into copper, we'll have copper turning into copper plus 2. And then that copper plus 2 being in solution is going to attract itself to that coin because the electrons are going to go across the wire. So the negative electrons are going across the wire from the left to the right, and since those negative electrons are coming across the wire, the copper plus 2 ions are attracted to those negative electrons, so they're attracted to that coin. So electrons are going from left to right, which means the left is the oxidation, which is called the anode, and the right is the reduction, which is called the cathode. So that's where reduction occurs. So you would think that zinc is the one that's going to be oxidized since it's lower on the chart, but zinc is actually reduced, and the copper is the one that is oxidized. So that's basically how electroplating works. Now let's look at some math problems to kind of work through what we can do with that information. So first we're going to need Faraday's laws, and we're not really going to use Faraday's law, which has to do with magnetic flux and current, but we are going to use some of his ideas, and his experiments had to do with magnetism and charge. So first we need some definitions. A coulomb is a unit of charge. This S here is SEC, that's a time, seconds. An amp is a coulomb per second. A volt is a joule per coulomb. Remember, a joule is a unit of energy. Current is equal to charge over time. For some reason, current is the letter I, charge is the letter Q, time is the letter T. The charge on one single electron, just one, is 1.6 times 10 to the negative 19 coulombs. So if you were looking at an entire mole of electrons, you would take that 1.6 times 10 to the negative 19 coulombs and multiply it by 6.02 times 10 to the 23rd electrons. And if you type that into your calculator, hopefully you'll get some number close to 96,500 coulombs per mole of electrons, which is called a Faraday, which is why we're calling them Faraday's laws, even though we're not actually using Faraday's laws. Let's see how this applies in a math problem. How much charge passes through the cross-section of a wire that's carrying 0.987 amps of current for 12.3 minutes? And remember that 0.987 amps is the same thing as saying 0.987 coulombs per second. That's supposed to be a second. So instead of using current is equal to charge over time and then converting units the way I should, I'm going to actually just do this as a giant factor label problem. So I really like to think of all of these as just giant factor label problems, and you can really just get everything that way. So we've got 12.3 minutes, and remember factor label is a way to cancel units, so the unit you have goes on the bottom and the unit you're looking for goes on top. Since an amp is a coulomb per second, I'm going to turn the minutes into seconds. 1 minute is 60 seconds. I am not looking for time, I'm looking for charge, so I'm going to move along, put seconds on the bottom, and then we noticed that we have 0.987 coulombs per second, so 0.987 coulombs per 1 second. And actually, that's charge. Right there, a coulomb is a unit of charge, so we're good. Let's solve that. So type in your calculator 12.3 times 60 times 0.987, you end up with 728 coulombs. So that is how much charge passes through the cross-section of a wire. Now it also says how many moles of electrons pass through this cross-section. So I'm going to keep going with that 728 coulombs. And I'm looking for how many moles of electrons, and we know that Faraday's constant is 96,500 coulombs is the charge on 1 mole of electrons. So 728 divided by 96,500, and really I just left that 728 in my calculator, I didn't retype it. I end up with 0.00755 moles of electrons. Let's look at another one. Calculate the quantity of electricity, or the charge, the coulombs, required to deposit 2.16 grams of silver from a solution of silver nitrate. So again, I'm just going to do this as a plain factor label problem. That way I don't have to worry about unit conversions and plugging into a different formula. 2.16 grams of silver. The way that factor label works is to put the unit that you start with on the bottom. So what do you know about grams of silver? Well, the periodic table says the mass of silver is 107.9 grams, and that's the mass of 1 mole of silver. But we don't really want moles of silver. I do know that the coulombs has to do with moles of electrons, so using this balanced equation, 1 mole of silver is 1 mole of electrons, and then using Faraday's constant, 1 mole of electrons has a charge of 96,500 coulombs. And that's my charge, and so I'm just going to solve 2.16 divided by 107.9 times 96,500, and I end up with 1932 coulombs. Let's try another one. A current of 5.0 amps is passed through an AlCl3 solution for 1,000 seconds. How many grams of aluminum will be produced? I think you might know enough right now to pause the video here and try this one on your own. Go ahead, pause it. Just try it. Did you pause? Okay, let's do it all together. Al plus 3 electrons makes Al. 5.0 amps is the same thing as saying 5.0 coulombs per second, and then 1,000 seconds. So I'm going to start with 1,000 seconds. And 5.0 coulombs per second is the number of amps that we have. And coulombs goes on the bottom. Okay, so what do I know about coulombs? Faraday's constant says 96,500 coulombs is 1 mole of electrons. We're not looking for moles of electrons, we're looking for grams of aluminum. So my balanced equation says 3 moles of electrons makes 1 mole of aluminum. 3 moles E makes 1 mole Al. And we're looking for grams, so 1 mole of aluminum has a mass off the periodic table of 27.0 grams. 1,000 times 5 divided by 96,500 divided by 3 times 27 equals 0.466 grams Al. All right, one more. This time, I'm not even going to read it to you. You're going to pause the video, read it to yourself, work it on your own, and when you're done, come back to me and we'll work through this problem. Okay, how long in minutes must a current of 3.5 amps, means 3.5 coulombs per second, be passed through a solution of copper sulfate to deposit 2 grams of copper? So I'm going to start with my 2 grams of copper. And the grams of copper can be changed to moles of copper, because the periodic table tells me that 1 mole of copper is 63.5 grams. So now moles of copper. And at this point I'm going to need a balanced equation, because I'm going to have to convert moles of copper to moles of electrons. Since it's copper sulfate, and sulfate is -2, that means this is copper plus 2. Be aware, because sometimes copper can be plus 1. Cu plus 2 electrons makes Cu, which means that there are 2 electrons for every 1 copper. Okay, so 1 mole of electrons has a current of 96,500 coulombs, or a charge, sorry, of 96,500 coulombs. And we're looking for minutes, time. Well, earlier we said there's 3.5 coulombs per second. So 3.5 coulombs for 1 second. And we're looking for minutes, which means 1 more 60 seconds is 1 minute. And typing it in, I end up with 28.9 minutes. Now these types of problems are really handy to talk about electrolysis or electroplating. How long will it take to electroplate this amount of copper? Or how much energy or how much current do I need? How much charge do I need? How many grams of copper am I going to do if I leave it for this amount of time? So that's what these things are really, really useful for. And that's Faraday's laws. We'll see you next time.